Hello, welcome back. Today we're going to start on structure 1.3. We are moving right along. This part of the syllabus is about electron configuration, so I'm going to talk about where the electrons are, what they're doing, why they're there. And our guiding question for this part 1.3 is how can we model the energy states of electrons in atoms? Electrons are super important. They basically do most of the interacting when we are talking about interactions between atoms, like between two different atoms, right? So, before we get too deep into electrons, though, we need to understand electromagnetic radiation. So, here's a couple questions. Which types of electromagnetic radiation are relevant in these contexts? So you can see there's some pictures here, right? We've got a microwave, a sunburn. These are like night vision goggles. This is like an MRI machine. This is your phone. This is an X-ray. Uh, and then what is different about different types of electromagnetic radiation? So see if you can pick out which types of electromagnetic radiation are being used in each of these. If you don't even know what this is, that's okay. You may have heard about this in physics or in your previous chemistry classes. But we're going to talk about what is electromagnetic radiation. But real quick, give it a try. If you're not sure, just give me your best guesses on both of these questions. So take a second and write down your answers. Okay, so starting here, the type of electromagnetic radiation that a microwave uses is microwaves. Microwave radiation, right? Sunburns are caused by UV radiation. Night vision goggles use infrared radiation. MRI or radiotherapy uses gamma. Your phone is using the visible spectrum, right? You can see what's on it. And then this is radio waves, or sorry, X-rays. Your phone also uses radio waves to communicate. This is an X-ray, right? So what is different about all these things? That's what we're going to think about and learn today. So this is first part of 1.3, the electromagnetic spectrum. So this is the electromagnetic spectrum, and it is important because it relates to electrons. We're going to see that we can discover a lot of things about chemicals and atoms and elements based on the light that they give off or take in certain circumstances. So we want to know what this is. The electromagnetic spectrum is a spectrum of radiation, right? You might think of it as light, right? Because we see a very small portion of it from wavelengths of 400 nanometers to 700 nanometers. But it includes all of these things, right? Radio waves, microwaves, infrared, the visible spectrum, UV, X-rays, and gamma rays. And like the sun is giving off all of these types of electromagnetic radiation all the time. And actually, chemicals, atoms, are also giving off electromagnetic radiation. Like living things give off infrared. It's because we have heat in our bodies, so we give off this type of infrared radiation. But my question here, right, is what is the relationship between the wavelength, so you can see wavelengths up here, and energy in the electromagnetic radiation? So this is wavelengths in meters. So you start over here. Radio waves are really big, 10 to the 8 meters. That's big, right? 10 to the 0 would be like 1 meter. And then it gets smaller and smaller and smaller. So think about the energy versus wavelength. What is that relationship? And look at the different types and think about which ones you think might have more or less energy. So take a second and try and answer that question. So It is an inverse relationship. That means as the wavelength decreases, as it gets smaller, right, the energy increases. Radio waves have very little energy. Microwaves have a little bit more, a little bit more. Is it light? UV has so much energy it can burn your skin, right? That's why you get a sunburn. X-rays have even more. They can penetrate your skin and look beneath. You can see bones. And then gamma rays are super high energy. These are very dangerous, right? Actually, all of these can be dangerous in their own context. And right here, real quick, these letters all stand for different colors, right? So this is violet, indigo, blue, green, yellow, orange, and red. Or if you flipped it around, it's Roy G. Biv. That's how I was taught how to remember this. Red, orange, yellow, green, blue, indigo, violet. So those are all associated with colors. So what is electromagnetic radiation? So it is radiation that has both electric and magnetic fields and can be modified or modeled, can be modeled as both a wave and a particle. This is called wave-particle duality. If you got far into physics, let's start talking about quantum physics. We get to talk about this. It's a really interesting thing, property of electromagnetic radiation. But for right now, you can just know that we can model it either way, right? We can model radiation as individual particles called photons, like little specks of light, basically, or as a wave traveling through space, a disturbance in this electromagnetic field. And yes, electricity and magnetism are connected. They are part of the same force. So the properties of electromagnetic radiation that we are most concerned with are the wavelength, which is, we use a symbol called lambda, and it is the distance between two peaks, right? So like here's a peak and here's a peak. The wavelength is just literally the distance between these, right? And we use the units of meters, and I think that's what's in the data book. So like, let's say there was 1 meter between these peaks. I'd have a wavelength of 1. Let's say there was half a meter between these peaks. Its wavelength would be 0.5 meters. And like, yeah, radio waves are really big. They can be a meter or bigger. As you get higher in energy, they get smaller and smaller wavelengths. The frequency is the number of waves that pass a point in a second. And its units are seconds to the -1, so 1 over seconds, or often we'll say hertz, each z. So the more waves that pass a point in 1 second, the higher the frequency. So like this has a low frequency. Within a second, you might only get 1 wave, right? Up here, maybe you get 2 or 3 waves within a second, so this has a higher frequency. So, how are wavelength, frequency, and energy related? We have a couple of equations here. These are important. We will do some calculations with these. This first one is C equals lambda times F, which is the speed of light, which is a constant, which means it never changes. And this would be the speed of light in a vacuum. It's always the same. Equals the wavelength times the frequency, right? So the speed of light of any bit of light, any bit of electromagnetic radiation, is always equal to this when it's in a vacuum, which is super, super, super fast. That's 3 times 10 to the 8th meters per second. And it is always equal to whatever the wavelength of that light is times the frequency of it. And then over here we have energy. So energy is E. Energy is equal to H times F, or Planck's constant, which is another thing that never changes, right? Times the frequency of the light. So Planck's constant is 6.63 times 10 to the 34 joules per second. So we can use these to help us calculate any of these variables, right? Because C is a constant, it won't ever change. H is a constant, it won't ever change, right? But if we then know the frequency of our light, we can use some algebra and solve for the wavelength, right? Or vice versa. Or if we know the frequency here, we can calculate the energy. If we know the energy, we can calculate frequency, right?